You're the expert, right?
Yeah.
That's the charger. Okay.
Yeah, start.
Ready to go? You have to click this thing here. Okay, so our next speaker is Raul Arias, and he will talk about gravitational observatories in AdS 4.
Thank you.
Take it away.
Let's see. The pointer is this one. Yes. Okay, thanks to the organizers for inviting me to give the talk. Something before to start. I didn't use a lot of references, so sorry if someone is not cited on the work on this thing. Also, I missed this. It's not 31. So sorry, dummy, because there are a lot of papers of you that is not cited here. And sorry, Don, also. There is some paper of you that is not cited here. And the rest, I don't know. So sorry in advance. Well, let's start. Ah, no, this has to be. I know what is it. Now? Okay. No, but also does not work from here. No. I can change from here, eh? I don't need this. Okay. It's okay. I don't know. I don't care. Like this is okay. So I will finish the romance with entanglement and start again with something that is not on flat space, but could be on flat space. I will talk about classical gravity, boundary conditions in classical gravity, just shear. But the motivation will be to study finite cutoff holography or understand, this is going to appear all the time. What I had to do, Herman, just to say it. Ok. Switch off the Wi-Fi. That is a smart thing. Die. Very good. Finite cutoff holography. What is this? We have AdS, the well-known AdS overall friend. It has an asymptotic boundary at infinity. What we are going to do today is to use another boundary before the asymptotic infinity and ask ourselves what boundary conditions we have to put there, and when we have the, let's say, good boundary conditions that I will discuss, see if we have what we can learn about finite cutoff holography. Yes? This is useful also for numerical GR, because in numerical GR you cannot impose boundary conditions at infinity. You have to put some time-like boundary, for example, and then you have to say which boundary conditions are you going to use. Also, interrupt me at any time. I don't care if I don't arrive to the end of the talk. Dummy is going to talk on Friday, so he can finish. Yes, Don, please. I'm very selfish. I'm going to learn more from all of you than you from me.
Well, is it really true that in numerical GR you can't work with the asymptotic boundary? You can't do you can't use, you know,
I believe
back-to-back
so.
coordinates and
I never did a very properly called numerical GR computation, but I think that at infinity you can't.
why not? Why can't you just
Tell to the computer.
Why can't you?
I mean,
why can't you choose a coordinate which is a compact range at infinity and work with the conformally rescaled manifold?
Honestly, I don't know. I never did. I just know the folklore of the people that I hear about this, saying that. For me, makes sense, but
Okay, so you say Franz Pretorius wouldn't try it.
At least I've talked with him about it, and he mentioned this as a problem.
Interesting. Okay.
very good.
I don't understand why, but I'd like to.
Very good. I think we have to. Okay. I will start from the beginning, what is called the initial value problem, because conceptually what I want to discuss, that is the initial boundary value problem, conceptually is the same. And this is something, the initial boundary value problem is something that is not very, at least I didn't find a reference that is very self-contained, understandable, at least for me. But as the initial boundary problem is conceptually similar, and this is chapter 10 of World Book, so you can learn from there and then extrapolate. I will start with Einstein equations in vacuum. I will also, along all the talk, the thing will be in the vacuum. No stress energy tensor. Lambda will be negative for us because in the second part of the talk I will talk about AdS4. But could be 0 or the zeta. So in 4 dimensions, these are 10 quasi-linear partial differential equations for the metric, and this is hard to solve. Also, you have to take in account that there are constraints that came from the Bianchi identities. So these are another 4 constraints, the momentum constraint and the Hamiltonian constraint. So you have to solve the Einstein equations and also satisfy the constraint equations. As an extra ingredient, we have, well, we all know that the form of invariants that make the things sometimes less clear. Which is the initial value problem? Suppose you have a manifold M. This is the space-time. This is, I mean, in the picture, it's a cylinder, but this is just pictorial. You have the whole space-time. Imagine the form you want. I will call M to the space-time manifold, and you. The question is if you have a Cauchy slice, space-like. In this case, is this sigma green thing. The problem, the question is this one: which kind of initial data we have to give at this Cauchy surface in order to obtain a predictive theory? In the mathematical sense, they call well-posed, because we want to do predictions with GR. And this was studied a lot in the 50s and 60s by Yvonne, Jorge Brujat, Riero, and more people. I will explain now what is well-posed. What it means well-posed. For me, it's for me and for some mathematicians, it is that you have to obtain a solution. You have to ensure that there exists a solution, and the solution is unique. These are 2 strong requirements. The solution has to be unique, has to be solution of Einstein equations, has to be solution satisfied constraints. Also, there is another sense of well-posedness, that is the Hadamard sense. Hadamard added another condition, that is that small changes in this initial data leads to small changes in the solution. So these people, in a very mathematical way, prove that the initial conditions that you have to give in order to be a well-posed, to have a well-posed problem on sigma, is to give the induced metric and the extrinsic curvature. Now, let's back to the initial boundary value problem. Now you think that in the previous slide, we have this infinite spacetime. Now I'm going to add also time-like boundaries, called gamma here. So I will cut the space. Now it's a box. It's not anymore infinity, this is a box. And we can ask the same question. Which boundary conditions we have to impose here in order to have a well-posed problem? Again, we want a solution that satisfies Einstein equation and the constraints equations on gamma. Good. What was proved in several papers by these mathematicians and Anderson was that Dirichlet and Neumann boundary conditions are not well posed. In general, there are cases, AdS is magic. In AdS it works very well, so Dirichlet. But in general, there is no. Now I will say why Dirichlet is not well posed. Well, fix the induced metric.
Before, so you fix either metric or extrinsic curvature.
You fix the metric, the induced metric on gamma.
Yeah, in Neumann boundary condition, you fix.
You use the extrinsic curvature, yes. And the ones that I will use is like a mixed thing. Yes. Only for k equals 0.
The Neumann boundary condition bad only for k equals 0, or is it true for, is it bad for all fixed values of k? I thought there was a statement on a previous slide that Neumann boundary conditions were problematic, which would be fixed. Okay, sorry, I'm sorry. If you fix pi, if you fix
KMN.
Right, and if you fix those to any value, it's a bad boundary condition, not just pi equals 0. Okay.
Both, Dirichlet and also Neumann. Yes. Here I'm just going to talk about Dirichlet because it's the most common. There is a failure of existence. If you fix the induced metric on the time-like boundary, in general, there are no solutions to Einstein equations that satisfies the Einstein equations, and this one of the, for example, this is the Hamiltonian constraint on gamma. And also, even if you insist and you find a solution, you can find also that it's not unique. So it's not a well-posed problem. Well,
I've always had this question about whether this is something that can be fixed up. I mean, I understand the Dirichlet case, what the problem is, but this is a lot like the linearization stability constraints that we live with all the time in the case of cosmology, right? Where there are linearized solutions that are not, in fact, that don't satisfy a quadratic constraint, and that, you know, there's data that doesn't lead to a full solution. But we don't give up on the problem. We just find another way to deal with it.
No, I agree.
So is this qualitatively different? Or is it just the statement that the usual, I mean, the theorem is true. If you give data, it may not have a solution, but does that mean?
No, I agree that you can relax or what you want. I mean, you can live with that. But if you want to be more mathematical, how is the word? If you think the mathematicians are gods, and you want to be like gods that tell you this is a theorem, this is not well posed, We are physicists and we can relax
theorem is
things.
true, but the question is, can we change the question to make a well-posed question?
For example,
again, with cosmology, there are linearization stability constraints. The initial value problem is, in its simple sense, is not well posed, but we know what conditions to impose on the data to make it well posed. I don't understand why we can't view this in the same way, why we can't impose a quadratic constraint on the data that would then tell us which infilling problems make sense. I just don't know what the mathematics is in that case, what the theorems are, and I'm curious if anybody's ever looked at it.
There is no solution, it's bad.
No, if there is no solution, this is bad.
Right, but if the problem can be seen at quadratic order, and if you would call it perturbation theory to quadratic order, you can tell which data is good and which is bad, you can salvage the thing. And the question is really, is there another new non-perturbative problem, or is it only this perturbative problem that you could see by working just at the boundary and then fix it? Because that's what you do for cosmology. You know what the constraints are, and you choose data that satisfies them. So I'm curious whether it's different. Right. I agree. Uniqueness is harder to fix than existence. Yeah. Okay.
No, it's okay. It's okay. The discussion is okay.
Do you know of anyone that has the ability to solve
I'm not aware. You are aware, Danny? I'm not aware of the Hamilton-Jacobi. If someone.
Yeah. So if the Hamilton-Jacobi approach has been applied to this question.
I don't think so. No.
No, so one thing is indeed, so if it's not possible, so there are certain situations indeed where the Neumann boundary condition is well defined, and then the Dirichlet boundary condition seems to have this problem. But if you can do things in the Neumann boundary condition, you can sort of derive a Hamilton-Jacobi functional as a function of the extrinsic curvature, and then the only thing you have to do is a Legendre transform.
Yeah,
and then you go between the two boundary conditions.
Yeah, for certain classes of Dirichlet, people do that trick to go from conformal to Dirichlet. For instance, if you have spherical symmetry,
right,
you can start from conformal boundary conditions that are well posed and do some Legendre transformation to go to Dirichlet, and those are well posed.
Right.
But generically, you cannot do that.
Okay.
So what the mathematician said is that what you have to be is the conformal class of the induced metric on gamma. You have to fix the trace of the Stephenson curvature. And also, it was found that in 2025, this year, I mean, it was fine before, but the mathematicians proved that they need also initial conditions on the corner, the intersection between the time-like and the space-like surface. There is proof that these conditions are well posed in Euclidean signature, also in Lorentzian signature. This year was also was this, and there is a warning here because we will see, and also it was seen in another papers by Dio, Dami, and Chawa, that there exists some modes that are unstable. And Liu and friends show that if you can cook up with these modes some solutions that violate the Hadamard conditions that I said before. You can violate the condition that if you do small changes in the initial data, you obtain small changes in the solution. So this is from 2 months ago, and it deserves more study, at least from my side. Other options that are not the conformal boundary conditions are the umbilic boundary conditions, studied recently also. where you have to impose this equation on gamma. And also there is a generalization, again by Liu and friends from last year, of the conformal boundary conditions, where you have to fix the conformal class of the induced metric, and also you have to fix this combination, the determinant of the induced metric to the p is some value between 0 and infinity, and when p goes to 0, you obtain again the conformal boundary conditions, and if it goes to infinity, you obtain Dirichlet boundary conditions. These two are well posed in the mathematician sense, and this is not well posed also in the Hadamard sense, because the proof of well posing of these conditions is the same as the Anderson and the same as the conformal boundary conditions proof. Well, the setup is clear. I mean, because maybe people at the beginning is confused that now you don't have an infinite space, you put some boundaries. And that is all. Now we are going to apply this to AdS4, these boundary conditions to AdS4. And what we are going to see is the apparition of some new boundary degree of freedom that is not present in the standard AdS-CFT and is alive here. It's live here that we have the boundary at finite cutoff. We will explore some implications. We are going to do linearized analysis. So let's see. Some general framework. I will have to write something also. This is the action, Einstein-Hilbert action, plus something like Gibbon-Hawking-York boundary term. As we change the boundary conditions, the Gibbon-Hawking-York boundary term is designed to have a well-variational problem of this action, the Einstein-Hilbert action, when you impose Dirichlet boundary conditions. Now, if you are imposing another thing, you have to see which is the term that makes the problem, the variational problem well posed, and then fortunately the change is just a factor. It's just a number here in front. It's like the Gibbon-Hawking boundary term, but it differs in a factor. This has implications when you study thermodynamics, for example, of a black hole. The boundary data, as I said, to fix the conformal class at gamma and to fix the trace of the extrinsic curvature that could depend on the coordinates on the time-like boundary. Well, here, in order to be clear with what conformal class means, this was written by Javi. I will not clean your ideas. If we have a metric, I will be honest. I wanted to write in this black one from Monday. It's very nice. It's very beautiful. What I want to say. We'll work with metrics of this form. Well, here we could be more general. Well, this is like the metric of could be a sphere, a flat space, whatever. When we say fix the conformal metric, if we, for example, put a boundary at R equal to R naught, if you read the paper, it will not be called R naught. It's a funny error that I don't like. What we are going to do is to allow So this is a condition. We are going to fix the conformal, we are going to fix, yes, the induced metric up to a function. And this function WB is the one that is going to be alive, is the Weil model. And also we are going to fix the trace of the extrinsic curvature. This is the idea. This is what I mean when I'm talking about conformal class. And again, this Weil model is this omega. So I show the Einstein-Hilbert plus the Gibbon-York-like term. With that, you can compute the stress energy tensor, but now for our boundary term that is suitable for conformal boundary conditions, was done also before. And you can see that the stress energy tensor has this form. It's traceless by construction, and if the trace of K is the trace of Kmn is constant, also conserved, you can apply this. What is this? If you AdS can be written in Fefferman-Graham like style. If you write it in that way and you impose conformal boundary conditions, you end up with this expression where this is transverse and traceless with respect to Gmn naught. And you can see now KL, well, some comment, KL equal to 3 is the standard AdS4 result. If you took AdS4 and you compute K, the trace of Kmn, of K mu nu, you end up that this is 3. So if you go to 3, you have to do holographic renormalization, and the result when KL goes to 3 in standard AdS-CFT is this one that is here. So we recover that. But now this is a term that outside of KL equal to 3, that is a parameter that we can use because we can put KL equal to 4. It's a boundary condition. We have this term. So it's something physical now. This is what I want to say, that there is something physical there. Now let's go to, this was the framework. Let's go to do linearized dynamics in global AdS4. This is the metric of the global AdS4. We are going to impose something like that. What we are going to say is that we have at the boundary that one this will be the conformal class. It's like omega equal to 0, but K has some expression in terms of the position of the time-like boundary. I lost it. So this is K. When you go with the position R naught of the time-like boundary to infinity, you obtain KL equal to 3. That is the AdS result. Well, we are going to linearize things, you know. And consider things that are in this way. We can use the Kodama-Ishibashi decomposition to study in a gauge-invariant way how these perturbations. So now I will just talk about the results. Now, a warning, this L is not LADS. On the slides, L is everything, but this is LADS. This is the Kodama-Ishibashi thing is to what does is to study these perturbations in irreducible representations over the sphere. So this L is the one of the spherical harmonics. For L equals 0, we can do the computation, these computations, and when we can compute this Weil factor. I mean, I will not do the computation, it's on the paper. You can study this, and when you arrive to the solutions, you have some diffeomorphism. Some of them are just in the bulk and does not move the boundary, and other ones arrive to the boundary and modify the position of the boundary, or at least fluctuates. This induces a change in omega. This omega was 0 here, but there is a delta omega that is alive because of, I mean, it exists because there is this diffeos, physical diffeos. And what we can see that the frequency is this one, and there are modes that are unstable. But this mode also, it's if you use the solution, you can see, you can compute this component, the corner component of the fluctuation of the fluctuation, and you can see that this is proportional to the time derivative of this object. So what we, in this example, this is an example where you see that on top of the conformal initial conditions, if you have to have the complete problem well posed, you also have to give initial data for omega and for the time derivative, the velocity of omega. So this is new. When you will go to the AdS boundary, when you take KL going to 3, this is decoupled from the bulk and is not dynamical. For L equal 1, I didn't say nothing because are all gauge. There are no physical diffeos that move the boundary. And for L greater than equal to 2, we can use the full power of this Kodama-Ishibashi expressions, formalism, and decompose the H mu nu in terms of a scalar and vector sector. If you follow this formalism, you can see that you end up with a master field equation, where this is the Laplacian of AdS2 for some field phi, and if you solve this, you solve the full fluctuations of the metric. So when you apply all this formalism to the conformal boundary conditions, you obtain allowed frequencies for this value. And you can see that there are some unstable modes for this is a picture for KL equal to 5, for example. You have these 4 modes there. And when you are going more and more closer to AdS, KL equal 3, that ones die and you have just real frequencies. Also, we see that there is a critical value for K. Well, this I say, but here you say that the imaginary part of omega time L, this L is LADS. This picture is for L of the spherical harmonic equal to 2. You see that the near AdS, this imaginary part is 0, but then as you are far away from the AdS boundary, moving K to higher values, you obtain a solution that is unstable. This is for the real part. The 2 modes, this for KL greater than some critical value, these first 2 real modes coalesces in this one, in just one. Then in the last part, this last part of the talk, I will just say some small things about the planar AdS analysis and also an Euclidean analysis. When you do planar AdS, I mean, this is not anymore a sphere. This sigma 2 is just planar. You can see that there are no complex modes. Even at large L, there are no complex modes at all. They are all real. And this boundary mode is pure gauge. It has some effect on the energy, but it's pure gauge.
What does it mean that a pure gauge mode?
No, it means that you don't need to give the initial conditions, as I said. I say you have to give the initial condition for in the previous case. You for L equal 0. You have the thing that as there are physical diffeos, you have to also give do the initial boundary value problem that you had. You also have to give initial condition for this, and you have to give initial conditions for the time for the velocity of this. This is in a spherical with a spherical boundary. With planar boundary, you don't have to give them.
Okay.
It's like the couple. I don't know. It's something like that. And lastly, if you do an Euclidean analysis, again in planar boundary, but in Euclidean in real time, not in real time, in Euclidean time, you can try to do the game that you always do in AdS-CFT and see which is the source for this new mode omega. And you can check that this source is K. Now here what we did is to put KL equal to the, K equal to 3 over L AdS plus delta K. And this is the delta K that is there. You can see that, and also you can, from the on-shell action, the standard computation, you can see that the Weil factor 2-point function is like this. It's like a massless scalar in 3 dimensions. At least in some sense suggests some AdS-CFT dictionary also, a finite radius. Lastly, about the Euclidean thing is if you are in AdS4 with an S3 boundary, you can compute the partition function set, and you obtain this result that goes like, again, this is the moral of this is just the same as I say for the Brownian stress energy tensor, that outside of KL equal to 3, this is something physical. And when you are in KL equal to 3, if you are doing standard AdS-CFT, you have to obtain a result using holographic renormalization. Here you don't need that. And I think I don't have much more to say. Just like a summary of the things that I already highlight. When you have finite size boundary, you change the phase space of gravity in the sense that you need these conditions for omega, that is a new Weil mode. And in some sense, there are these instabilities that we found signal some breaking of conformal symmetry at the boundary. That is standard also in TT bar deformations. Then one of these questions is this related to TT bar deformations somehow, in some way? Another question is, what is the holographic dual of this omega? But the more maybe fundamental question at this point is, well, if these boundary conditions are truly well posed in the sense of these papers of Ann Anderson and now the new things about Liu and friends. And a last dream, let's say, is how if these are well posed, so you can take this de Sitter and put some time-like boundaries and these conformal boundary conditions on that time-like boundaries. So could be this some way to DS holography or also flat space holography? Well, that's all. Usually, in the last slide, I have a picture of Messi. I have respect for Brazil. They have 5 World Cups, so today is not here.
Okay, thank you. Are there questions still? For questions?
Hi, very nice talk. So, what I understand, like, is it similar to the problem of solving Hamiltonian constant on a radial slice in AdS? Like, is it similar or different? Or like, I just wanted to mention that there is this literature of this holographic renormalization where they have some version of this, some reconstruction at some boundary, but I think they're not in the finite, but like close to the boundary, like they are like solving the constraints on a slice which is like close to the boundary, maybe not the finite. So maybe it is some, so they have this omega, you are writing this dynamical variable omega, I think they're pushing that omega tends to infinity, so it's on the boundary. So is there any relation to those things?
I don't know, but I will say that if you, I don't know if in that computation something changed when you, if I'm purist, I will tell you if you put the boundary outside the AdS boundary before, you have to use these boundary conditions. I don't know if these boundary conditions changes the computation you are talking about, honestly.
I see, thanks. Okay.
I'm still not sure I understood what the deal with the dynamics of omega is, because you impose some boundary conditions and then you solve the problem. And why do you call omega dynamical?
Well, in the sense that I didn't, this is not the full paper. The full paper has also nonlinear analysis, and in the nonlinear analysis you have an equation of motion for this omega. In this linear analysis, delta omega, let's say, I mean, you have this. Imagine you have this with
but
omega.
This is a bit like in AdS CFT, we have the non-normalizable and the non-normalizable
This
modes.
is something,
we fix the so this is like a normalizable mode in some sense in that language.
It is
that
something like that, but not at the asymptotic boundary. So I don't know which interpretation could be.
Say again?
Will be staying the radial volume. And when you put it in some finite volume, you will have some equation of motion, and the dynamics will need initial data that will not be specified by the usual initial data that is involved. So it's only the conventional components of the metric and the specific curvature. And the velocity of the omega will come in the corner term that is neither initial nor boundary.
So it's an extra piece of phase space that is purely associated to the corner term somehow?
Yes, yes.
So omega becomes a variable because of the corner.
Yes.
That was my question.
Well, I feel like I should remark that I think whether you call it new or not is a matter of semantics, because it's like it's like a piece of extrinsic curvature at the corner. It's like a delta function term in K, if I understand correctly. Well, it has to do with okay. I don't know. New is a matter of semantics. It has to do with the angle at which the initial data slice intersects the boundary, right? Okay. All right.
But the initial problem, you fix the volume with metric, and with compatibility with the initial data, you just fix
The whole thing.
here.
Okay. There's an extra one. But what I wanted to ask is,
new maybe.
I got confused about what you were saying about the well-posedness of the IBVP. I do understand that the nonlinear problem is open, but did you agree with the recent paper by Liu, Real, Santos, and Wiseman that the linear IBVP is not well-posed?
Well, in the Hadamard sense, it's not well posed, I guess. But for the mathematicians, this is well posed.
No,
because
it's not.
they don't like.
It's not well posed. They proved this in the mathematician sense, right? I don't think there's a.
Maybe.
Okay.
Uniqueness and existence is going to be opposed. It's not Hadamard in the same continuity.
It's not continuous.
Yeah.
Indeed.
I thought that also meant it was not unique in a certain sense. That uniqueness failed.
No, this is.
Find multiple solutions that have the same initial data.
That sounds like it's not unique. You said there are multiple solutions with the same initial data. Okay. I'll talk to you more later to find out.
Yeah, please. How generic your data is.
The radial profile of this mode will concentrate on the boundary and the limit of infinite angular momentum will be purely boundary. So if you think of initial data that operates in the following process class, most probably that is inside.
I think that's the question of, can you work in some different kind of Sobolev space that gives you a different notion of continuity where continuity holds? That's certainly an open possibility, sure.
I think he wanted to know something.
Yeah.
I saw you.
It's, I think, related probably to the first one, but just because you mentioned that the gravitational phase space changes and the conformal, the CFT kind of becomes unstable, is this problem of doing AdS CFT at a finite boundary somehow similar to doing the usual one where at the asymptotic boundary now you still have Dirichlet on the metric, Dirichlet boundary conditions, but it doesn't have to be conformally flat. Like in AdS4, this is what, this captures radiation at the boundary, for example, no? Like it's the cotton tensor. So is this set up where you move the boundary to a finite slice, but you impose Dirichlet, which is still conformally flat? Somehow the same problem as still doing things at asymptotic infinity, but not using flat. Because the same things happen.
Now
you don't have
radiation
CFT
can
anymore.
travel also along the time-like boundary, right? If you put Dirichlet, you don't have that freedom. Because now this has some life, no? You can have a boundary that do that, and it's not fixed. I don't know if your question was.
No, okay, no, okay. Yeah, I was because also in that case the CFT does not. It's not the.
It's not a CFT.
Yes.
Yeah.
Okay, one last question.
So there is this old paper by Busso and other people, like I think they're saying like if you try to calculate something for some finite, just like in finite region in space time, you get some large fluctuations, etc. Something, there's some old paper by Busso and this group. So is it related to these instabilities, etc.? Like I don't know.
I don't know. I don't know what. I'm not aware about the result you told me.
Okay.
Okay, let's thank Raul again, and then we start lunch. Unless there's any announcement. No, we're good. Usual lunch. Okay.